Hi guys, I'm Mrs. Raposa and I'm going to be going over with you the squeeze theorem, and I'm working on page 8 in the note packet, so please flip to page 8. And what the squeeze theorem says over on the top left, it says if f of x is less than h of x, which is less than g of x. So h is in the middle. When x is near a, and the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x. So there's two outside limits are the same, and what they happen to be is L. Then the limit as x approaches a of the middle function, which is h, must also be L. So there was a lot going on there. So let's take a look and see what the squeeze theorem looks like on a graph. So over here on the right on my graph of f of x is down here. And it just needs to be the bottom function. Then h is in the middle. So h could look like anything, but it has to be in the middle. And then my upper function is g of x. And again, it could look like anything, but it needs to be up top. Also, in order for this to work, at A, and this is an A, that's kind of hard to see, but at A, the limit as x approaches A of my upper function and of my lower function, so of my blue and my green, both should be the same value. And in this case, they're both L. Then the limit as x approaches A of the middle function is also going to be L. Okay, this theorem is called the squeeze theorem because we squeeze the middle function in between the top and the bottom. And if you read the paragraph below, it says, the squeeze theorem, or the sandwich theorem, sometimes it's called, is used on limit problems where the usual algebraic factoring, conjugation, algebraic manipulation, etc., when those usual things are not effective. However, it requires you to be able to squeeze your problem in between two other simpler functions whose limits are easily computable and are equal. Okay, let's try it with a problem. So problem number 1 says, suppose that there are 3 functions. So I have 3 functions and h is right there in the middle of my 2 functions. And it says where x is near 2. Further, suppose that f is negative 1/3 x cubed plus x squared minus 7/3. And g is the cosine of pi over 2x. So g is my upper function and f is my lower function. The question is asking to find the limit as x approaches 2 of h of x. So in order to do that, since h is in the middle of f and g, we are first going to find the limit as x approaches 2 of f of x. Well, to find that limit, all we're going to do is substitute 2 right into that function f of x. So let's try to simplify this. Negative 1/3, 2 cubed, plus 2 squared, minus 7/3. Let's try to do it without a calculator. 2 cubed is 8, so this first term becomes negative 8/3 plus 4 minus 7/3. Now, without my calculator, I would combine my fractions together. So negative 8/3 minus 7/3 is negative 15/3, or negative 5. I still have plus 4, and so I get negative 1. So my limit as x approaches 2 of f of x is negative 1. That was my lower limit. Now I'm going to do the same thing for step 2, except I'm now going to use the limit as x approaches 2 of g of x, which g of x, remember, was the cosine of pi over 2x. So let's try to find our limit. And again, we're just going to plug right in. So equals the cosine of pi over 2 times 2. We're plugging 2 in, which is just the cosine of pi, which is negative 1. So I found my upper limit to also be negative 1. So remember, back at the top, H is in between these guys. So if my lower limit is -1, and my limit of the function on the top is also -1, what conclusion can we make about the limit as x approaches 2 of h of x? And the conclusion that we can make is the answer here is also -1. If my function on the bottom has a limit of -1 and my function on the top has a limit of -1, then the actual limit is going to be -1. Okay, let's try another one. In fact, I'm going to skip over number 2. It's the same idea here. It may or may not work. And it's actually, I'm going to let you know, it doesn't work here. My lower limit and my upper limit turn into different values. But let's try number 3, because number 3 looks way more complicated. Number 3, it says, find the limit as x approaches 0 of x squared cosine 1 over x. And this is how a typical problem would come, just like that with no other information. And so we might try to plug 0 in, but if you plug 0 in, we have a problem here because the cosine of 1 over 0, we can't divide by 0. So it does not work to plug in. So I have to think of an alternate method. The alternate method I'm going to use is I'm going to try to use the squeeze theorem because I can't factor or conjugate this or any other methods I know how. So when trying to find functions to use to squeeze h of x, we start by isolating the most complicated part. So let's look at our problem and let's look for the most complicated part. And I think when I look at this, that my most complicated part of this is the cosine of 1 over x. And that's actually the problem, the x there in the denominator. Also, if you read this sentence here, it says, when one part of h of x is sine or cosine, we should choose that. We should choose that as our inside piece, or our part to isolate. And the reason that we choose that is because those functions have a restricted range. So I want you to think about a cosine graph for just a moment. And our cosine graph looks like this. And the restricted range for any cosine, and this is true for sine as well, is my cosine graph is always going to stay between -1 and 1. And so therefore, in this case, we choose to begin with the cosine of 1 over x, because we know that the cosine of anything stays between -1 and 1. So look at this statement that we can make. We pick our complicated part and we put its restrictions on. And we put those restrictions on again because we know that all cosine functions have to stay between -1 and 1. Now, that's not what the original problem looked like. So to return to the original or the given function, we need to multiply all sides of this inequality by x squared. Watch when I do this. This middle function is missing an x squared. If it said x squared cosine 1 over x, we'd be good. Well, I can't just multiply that by x squared. So I'm going to multiply all sides by x squared. And look at what I get. I get this. Okay, now how am I going to use this to help me figure out what the limit as x approaches 0 of the inside is? Well, this is our original function in the middle. It is bounded by -x squared and +x squared. So what about if we try to find the limit as x approaches 0 of the left side? This left side. And if I plugged 0 in, -0 squared is just 0. And then if I did the same thing in step 2, but I used the upper function, the x squared, right here, I would get 0. So I just found that the limit as x approaches 0 of my left-hand function or my bottom function is 0. And the limit as x approaches 0 of my right-hand or my upper function is 0. So in step 3, that must mean that the limit as x approaches 0 of this middle function must also be 0. And I have a graph here. This is way zoomed in. But on this graph, on the top, I have x squared, the function x squared. On the bottom, I have the function negative x squared. And in the middle, that green squiggly graph, it's oscillating, but that green squiggly graph is the graph of x squared cosine 1 over x. And as x approaches 0, right here in the middle, as x approaches 0, my limit is going to be 0. Okay. Let's try one more. So let's try problem number 4. So in problem number 4, it says the limit as x approaches 0 of x squared e to the sine x, e to the sine of 1 over x. And so we need to use the squeeze theorem to help us. So remember, we always are going to start with the most complicated part. And actually, I shouldn't say that. What we should start by trying to do is plugging 0 in, because that's what we always do for a limit. But if we went and tried to put 0 in, we would have an issue because we can't divide by 0. So we can't do that. So instead, we're going to use the squeeze theorem, and we're going to pick our most complicated part. Remember, if your function has a sine or cosine in it, we want to choose that as our most complicated part. So I'm choosing the sine of 1 over x as my complicated part. And I know that all of my sine graphs will stay always in between -1 and 1. So I can always bound a sine or a cosine graph like that. All right, now I really need for my graph to look like the original, which it's missing an x squared and it's missing a base of e. So the first thing I'm going to do is make the base e on all sides of this inequality. So I'll make it e raised to the -1, e raised to the sine of 1 over x, e raised to the 1. I'm still not back at my original function. Remember, this is my whole original function. I'm almost there in the middle, but I need an x squared. So the next thing that I'm going to do is I'm going to multiply all sides by x squared. So x squared e to the -1 less than or equal to x squared e to the sine of 1 over x less than or equal to x squared e to the 1. And now we've got it. We have our middle function exactly the same as the original. So in order to use the squeeze theorem, we're going to find the limit of the function on the left. So this function right here. We're going to find the lim as x approaches 0 of x squared e to the -1. And if I were to plug 0 in for x right here, I would get 0 times e to the -1, which is just 0. And then I'd find the limit on the right side. So I'd find the limit as x approaches 0 of x squared times e. And if I do that, if I plug 0 in to find that limit, 0 squared times e is just 0. And so because my lower limit and my upper limit were both 0, I can say therefore, remember 3 dots in a triangle mean therefore. Therefore, the limit as x approaches 0 of x squared sine of 1 over x, that was my original, must equal 0. And so my final answer, oh, that was fancy. My final answer is going to be just 0. So that is the squeeze theorem.